Alright, so the last problem I'd like to talk about before we move on to some problems with pendulums is this problem, and it's basically a vertical oscillation. So let me draw a diagram. So first we have a spring with a K spring constant, and it has this length L, and then a 209 gram block is now hanging on it. So basically it's at an equilibrium position. Okay, and then basically this is L plus equilibrium. But then it's pulled down to a point where basically it is like, say this is equilibrium. So basically this entire thing is 30 centimeters longer than the unstretched length. So L plus 30. And then this would just be L plus equilibrium. So basically we're trying to find the speed and velocity after 3 seconds. So basically, whatever you do, do not use 30 or L plus the equilibrium as the amplitude. That is not correct. So the amplitude is right here. It's this length. And what that is that is actually 30 minus the equilibrium, um, because this is the remainder of what is left of L plus 30. And when you add these together, the equilibrium positions cancel out, and then you get L plus 30. But to find equilibrium, where the position equilibrium is, so we have to use force balances. So at rest, this is the force of the spring, and then this is the force of gravity. They had to equal each other, so Fg has to equal Fs. So basically have to do Kx equilibrium equals mg. So we get x equilibrium is equal to mg over k, or if you want to rewrite it as g over w squared, go at it, but I wouldn't recommend it. So we know our x equilibrium, and oh, I'm sorry, this is supposed to say position. And yeah, so now we can and we know that um, the amplitude is 30 minus equilibrium, and at t equals 0 it starts at 30 minus equilibrium. But the thing is, since it's below the equilibrium point, so let's try to find the phase constant in this case. So basically, the amplitude, this is negative a, and then this would be positive a if you were to go up. So negative a equals a cosine w times 0 plus phi. You get negative a equals a cosine phi. So this is the amplitude, but it's below the equilibrium position, so it's negative. So when you take the arc cosine, you get phi equals pi. So yeah, now we are actually, so now we should actually find the angular frequency, and we're actually given enough information to do that. So we're gonna use the equation t of the period of the spring equals 2 pi over um, times the rad of m over k. So yeah, whatever value you get. So we get x of 3 equals um, amplitude, which is 30 minus the equilibrium position, and then times cosine. And also, I think it would be, since k is in Newton meters, it's better to convert this all to um, meters when you can, and then convert it back to centimeters. So we're gonna use 0.3 instead of 30. So because you have to have the units match. So and then cosine of 2 pi. So angular frequency is 2 pi over 2. So over 2 pi rad mk, and then times t plus pi. All right, and then I'm gonna rewrite this. So x of 3 equals 0.3 minus equilibrium, and then cosine of 2 pi over 2 pi m k, and then plus phi. So the 2 pi's cancel out, and then you can flip their reciprocal. So it's 2x of 3 equals 0.3 minus equilibrium times the cosine of rad k over m plus phi. So this is the same thing as x of 3 equals 0.3 minus mg over k, and then multiply by 2, my bad. And then times the cosine of 3 rad k over m plus pi. So I'm going to plug more stuff in. So x of 3 equals 0.3 minus mass, um, 0.219 times 9.8, and also 9.8 meters per second. So again, need units to match. So over 16.5, and then times cosine of 3 rad 16.5 over 0.219, and then plus pi. So you should get an answer of about negative 0.1047 meters. But because the answer is going to be in centimeters, we have to convert that. So then we should get an answer of negative 10.47 centimeters. All right. So next we're gonna have to find the velocity at time equals 3. So again, I'm gonna use conservation of energies, but you can use derivatives you want. So we get 1/2 kx squared. This is at t equals 3. and then plus 1 half mv squared. This is at t equals 3. And then equals 1 half, um, and then I'm going to do 1 half ka squared. And then a is just um, basically 0.3 minus equilibrium. So same gist here. So 1 halves cancel out, so you get kx squared plus 1 half, plus mv squared equals ka squared. I'm going to bring the kx squared to the right side, so we get mv squared equals ka squared minus kx squared. And then I'm gonna simplify this to be v squared equals w squared a squared minus x squared. So we get v equals w rad a squared minus x squared. So basically for this actually you should make sure that the amplitude and the what's it called, the position at time equals 3 have the same units. So either convert x to meters or a to centimeters. It doesn't really matter. But when you have matching units, you should get a velocity of about 106.2 centimeters per second.